State and prove the Gauss's lemma. Let P be an odd prime and let greatest common divisor of A and P equals to 1 if n denotes the number of integers that leave negative list residues in the set S equals to A, 2A, 3A, so on, P minus 1 upon 2A, then A upon P is equal to minus 1 raised to power n. Since greatest common divisor of AP is equal to 1, each of the integers in the set S are co-prime to P and no two are congruent to each other modulo P. Let R1, R2, Rm be these remainders obtained upon dividing by P such that 0 is less than Ri is less than P upon 2. Let S1, S2 and so on Sn be those remainders of such that P is greater than Si is greater than P upon 2. Then m plus n equals to P minus 1 upon 2 and the integers R1 so on Rm Ps minus 1 so on Ps minus Sn are all the positive and less than P upon 2. To prove that these integers are all distinct, it is sufficient to show that no of Ps minus 1 are equal to any of Rj. Let us assume that Psi equals to Rj for some choice of I and j. Then there exist integers h and k with 1 is less than equal to of h and k is less than equal to of p minus 1 upon 2, satisfying Si congruent to Ha modulo p and Rj congruent to Ka modulo p. Hence h plus k into A is congruent to Si plus Rj equals to P congruent to 0 modulo P, which implies that h plus k is congruent to 0 modulo P, but there does not exist such a congruence because 1 is less than h plus k is less than equal to of P minus 1. Thus P minus 1 upon 2 numbers R1 so on Rm Ps minus 1 so on Ps and P minus Sn are simply the integers. Thus their product is P minus 1 upon 2 factorial. So P minus 1 upon 2 factorial equals to R1 so on Rm Ps minus 1 so on Psn P minus Sn is congruent to R1 so on Rm into S1 minus S1 so on into minus Sn modulo P congruent to minus 1 raised to power n into R1 into R2 and so on Rm into S1 so on Sn into Sn modulo P. But we know that R1, R2 and so on Rm, S1 so on Sn are congruent modulo P to A, 2A so on P minus 1 upon 2A in some order, so that P minus 1 upon 2 factorial congruent to minus 1 upon 1 raised to power n into A into 2A so on into P minus 1 upon 2A modulo P congruent to minus 1 raised to power n a raised to power p minus 1 upon 2 into p minus 1 upon 2 p minus 1 upon 2 factorial modulo p, but p minus 1 upon 2 is a relatively prime to p. Cancelling p minus 2 factorial from both sides, we get 1 is congruent to minus 1 raised to power n a raised to power p minus 1 upon 2 modulo p. Multiplying both sides by minus 1 raised to power n, we get minus 1 raised to power n congruent to a raised to power p minus 1 upon 2 modulo p, or a raised to power p minus 1 upon 2 congruent to minus 1 raised to power n modulo p. Using the Euler's criteria, we have a upon p is congruent to a raised to power p minus 1 upon 2 is congruent to minus 1 raised to power n modulo p, which implies a upon p is equal to minus 1 raised to power n.